Okay, so yesterday we spent the entire period discussing acceleration. Today's sort of the tail end of that and a little bit more kind of thing. So you can just sit back and relax for a minute or two. And I'm starting. So Galileo was the first real scientist to sort of do some studies into motion. Aristotle had a lot of beliefs about motion. They were unfortunately all wrong, and people believed them for 2,000 years. I do have a short little video to show you about Galileo. So Galileo was the first scientist to clearly understand the concept of acceleration. He found that the acceleration of a ball rolling down an inclined plane and the acceleration of a falling object were both described by the same mathematical rules. And if you want to sort of read about Galileo, there he is there. Known as the father of science, the father of modern science. He did a lot of things. He was born in 1564, died in 1642, oddly enough the same year that Newton was born. Basically what happened was he did a lot of, he brought science into the new age. Science had been in the dark ages for a long, long time. He was the guy that sort of first did any sort of experiments. Now I ran across this just the other day. This is a fellow who was actually in Italy. If you ever go to Italy, there's lots of things to see, but there's also a museum called the Galileo Museum where you can actually see some of the equipment that he used. And I'm not going to read this for you, but you can actually see parts of Galileo. His fingers and part of his vertebrae, apparently, are on display. If you're interested in famous people's body parts. I don't know. Okay, there's the bridge that leads to his museum, I believe. There's a sculpture of Galileo. Here it is here, actually, here. When entering the Galilean room, you are met by... I'll just make this a bit bigger.
Whose power is fingers preserved?
I don't know. It's a good question. I know it's just his bones, I think. Yeah. Where is it? When entering the Galilean room, you are met by 3 glass-enclosed bell jars that house probably the oddest yet eeriest of all displays in the museum, Galileo himself. Because of Galileo's status as a revered scientist and statesman, grave robbers and souvenir seekers wanted remembrance of the famous scientist and raided his remains. In other words, they dug up his grave. Preserved under glass in what could only resemble a saint's reliquary, and I don't know what that means, are Galileo's vertebrae, molar, thumb, and middle finger. An ironic gesture to the world that he was right all along about the motion of the Earth and its place in the solar system. Kind of amusing. Okay? So here is a couple of pieces. This is actually Galileo's inclined plane that he did experiments on. You can see that you can't really get an idea for the scale of it, but it's really, really big. Okay, that's this thing here. Okay, this is a second experiment that he did. He was talking about whether the ball, whether it would take longer to roll down there or whether it would take longer to go on the curved path. Okay, here's his ramp. He used bells to indicate when the ball had reached that point, and we're going to talk about this ramp today. So this is what he built.
Wouldn't it slow down a little bit?
It probably would, yeah. You'd think so, yeah. I don't know. I guess it depends on how much of that touches. Okay. Here's his original telescopes that he made. Original projectile motion diagram. Here's kind of a neat thing. This is something that we actually do in grade 12. We actually do projectile motion and we calculate where to place the rings so that the ball will go through them. It's kind of a cool thing. Our equipment isn't quite as elaborate as this, quite as artistic. Okay, here's his chemistry bench.
He must have had a lot of free time.
He did, and you'll see in the video here why he had so much time. These are lodestones, which are natural magnets that he was using when he studied magnetism. You guys have probably all seen something like this before. Yeah, so that's his original one. What do you think these are for down here, these white and black? I'm wondering if that was put on after. I'm thinking it's so that when you can see the contrast, right? Like if you're taking a picture, you would sort of like the strip you see at the doors at 7-Eleven, you know, how tall you are, that kind of thing. I'm thinking that Galileo didn't put that on there. Okay, this is a force vector table. Not sure data was there. Okay, so let me see if I can find this video here for you. Did I not load it up? I thought I loaded it up.
You need to take notes.
No, you just need to sit and watch. Okay, this is the table of values that you need to be looking for. Okay, so this is just a sort of a picture of a ramp, much like Galileo's. You'll notice that it starts right here at 0 seconds, right? How far does it go in the first second? 0.5. Where is it at after 2 seconds? 2 seconds, or 2 meters. Where is it at the end of 3 seconds? 4.5, and then 8, and then 12.5. And you can clearly see that the distance between each one of these is getting bigger and bigger and bigger. How come? Because it's speeding up, okay? So what Galileo was most interested in is what are the mathematics behind this? And that's what we're going to look at right here, okay, sort of from a data standpoint. So if you look at this data table down below, okay, interval number 1, 2, 3, 4, 5, that refers to 1, 2, 3, 4, and 5. You might want to jot that in, right? Interval numbers between there and there is 1, there and there is 2, there and there is 3, there and there is 4, and there is 5. Interval numbers. Okay, now there's a lot of data going on here. Let me explain what's going on here. Okay, the next column is the time at the start of the interval. So the time at the start of interval 1 is 0. The time at the start of interval 2 is 1. The time at the start of interval 3 is 2, and so on. It's kind of hard to do. But it goes 0, 1, 2, 3, 4. In other words, each interval is how long? 1 second. So you need to put the phone away. Okay? What's the time at the end of the interval? Well, it's also going to be 1, 2, 3, 4, 5. Notice how the time at the end of this interval is the same as the start of the time of the next one, right? Okay, now, where does it start, the interval? It starts at 0, and then it starts at 0.5, and then it starts at 2, and then it starts at 4.5, and then it starts at 8, and then it starts at 12.5. Right there, 0, 2.5, 0.5, 2, 4.5, and 5. What's the position at the end of the interval? Well, it's simply, right, the end of this interval is the same as the start of that one, just like the time. Okay? Now, the next one is important here. The distance traveled in the interval. If it starts at 0 and it ends at 0.5, how far does it go? 0.5. If it starts at 0.5 and it goes to 2, how far did it go? 1.5. If it starts at 2 and it ends at 4.5, how far did it go? 2.5, right? These numbers are going up. That's the length of that one and that one and that one and that one and that one, right? That's those lengths. Okay. So, I take the distance traveled and I divide by the time. Right above this column, I'd like you to write V bar equals D over T. Okay? What was its speed during that interval? Well, how far did it go in the first interval? 0.5 meters, right? Right there. It went 0.5 meters. How long is the first interval? 1 second. 0.5 divided by 1? 0.5. How far did it go in the second interval? 1.5. Divided by 1, because each interval is 1 second. Its speed is now 1.5. How far to go in the third interval? 2.5 meters in a second. Its speed is now 2.5. What's happening to the speed right here, this column? It's speeding up. It's going 0.5, 1.5, 2.5, 3.5, 4.5. How come it's speeding up? It's accelerating. It's going downhill, right? It's speeding up. Okay, so that's my average velocity. Now, watch closely here. The instantaneous velocity at the start of the interval, okay? Think about tests and averages, okay? Keep that sort of in the back of your head, kind of. If I averaged 0.5, the average velocity is 0.5. Now, clearly, I started this whole mess at 0 meters per second, right? I started at rest? Okay, so that is my 0 right there. I started at 0. If I averaged 0.5, then what's the speed at the end of this interval? Let me just zoom in on this right here. Let me just zoom in a bit here and show you. Okay? If right here my speed is 0, and my average speed in between there is 0.5, well, how fast do I have to be going to average 0.5? If you got 0 on the first test, and then I told you then you wrote a second test, and I said, well, your average is now 50, and I didn't tell you what you got in your second test, what did you get in your second test? How do you know that? Because the average is 0 and 100 is 50. If I started my initial velocity right here at 0, and I averaged a speed of 0.5, what do I have to be, how fast am I going at the end? Am I not going 1 meter per second? What's the average of 0 and 1? 0.5. Okay, that's what they're showing down here. Right here. Okay, I average 0.5. Brett, you need to watch here, not erase. If I'm averaging 0.5 and I start at 0, how fast do I have to be going at the end? I got to be going 1 meter per second, right? Because the average of 0 and 1 is, what's the average of 0 and 1? 0.5. Okay. We've established that I'm going 0.5 at the end of that interval, which means at the start of the next interval, I have to be going 1. I've already figured out that my average is 1.5, so what's the final number? Like, what's the average of 1? If the average of a number and another number is 0.5, and the first number is 1, what does that second number have to be? 2. What's the average of 1 and 2? 1.5. And if I ended up at 2, then I start the next interval at 2. And if I'm averaging 2.5, then what do I have to end up that interval at? 3, because the average of 2 and 3 is 2.5. And if I ended at 3, then I have to start the next interval at 3. And if I average 2.5, then I have to end up at 4, and so on. Okay? And what is happening to the speed at the start of the interval? It's going 0, 1, 2, 3, 4. And at the end, it's going 1, 2, 3, 4. It's speeding up. All right, last little bit here. Right above this, A equals delta V over delta T. A equals delta V over delta T. How much did the velocity change? It went from 0 to 1. How much of a change is that? 1. In how long? 1 second. What's 1 divided by 1? The average acceleration then is 1. If I started at 1 and then I went to 2, how much did I change by? 1, and Nick needs to put his phone away. And that happened in 1 second, which means my acceleration is 1. And if I started at 2 and I ended at 3, I changed by 1, and it happened in 1 second, so my average acceleration is 1. And the average acceleration is a consistent 1 meter per second squared. Why is it a consistent 1 meter per second squared? Because the ramp is straight, right? It accelerates at the same rate down the ramp. So even though the speed goes 0, 1, 2, 3, 4, what does the acceleration do? It stays the same. It stays the same. Okay? Now, Galileo's idea was that this would relate to, and I'm just going to make myself some room here. Okay? He really wanted to take, the Leaning Tower of Pisa thing, right? He really wanted to take the big cannonball and the small little wooden ball and drop them at the same time and see which one landed first, which he did do, by the way. Okay? Would they have landed at exactly the same time? Probably not, because, there's some air resistance and there's all that kind of stuff, right? And it all happens really, really fast. You certainly can't just do it in a broom, right? Drop from this height. So his idea was that if you would roll it down a ramp, like what should gravity be? What's the number for gravity? Anybody know? 9.8, right? But when he did it down the ramp, he got an acceleration of 1 meter per second squared. But if he went at a steeper ramp, he could probably find an acceleration of 2 and 3 and 4. And in fact, if the ramp was steeper and steeper and steeper, if you got it to this point, well, it's almost what? Almost straight up and down. In fact, he said there's really, from a mathematical standpoint, there's no difference whether I roll it down that ramp or if I just drop it straight down. But by doing it at such an angle like this, he could do what? Slow it down so he could measure with a little pendulum thing, because he certainly didn't have a stopwatch. Okay. Guess what you guys are going to do tomorrow?
We're gonna do that.
You're going to do this.
Oh, yeah.
You're going to do this.
You get to use stopwatch.
You get to use stopwatches, yes. You get to use stopwatches. You've got a handout here. There was a group of university students who actually decided they wanted to go out and actually build a Galileo's ramp. Now we're just going to use my little wooden runs, right? They went out and they built Galileo's ramp, and they decided to try and do what he did and see if they got the same results. And this is sort of their little report. This comes from Rice University.
What was the ramp?
So it says, even using equipment that we might call simple or even rudimentary, Galileo revolutionized basic scientific principles which were posited by Aristotle. What do you think the word posited means?
Not negative.
Okay, now get your phones out. What does positive mean, Nicholas?
Says assume as a fact or put forward as a basis of argument.
Okay, so in other words, when Galileo revolutionized basic scientific principles which are posited by Aristotle. So in other words, Aristotle said, these things are true because I say them to be. And everyone agreed with him. And no one bothered to try to do an experiment. Okay? One of his most important experiments was the inclined plane experiment. Galileo used his inclined plane, a simple board with a groove down in which he rolled a small metal ball to examine Aristotelian ideas about motion. Galileo's inclined plane experiment radically changed these ideas by concentrating on acceleration, a stage of motion ignored by Aristotle and most of his followers, mainly because they didn't understand it, and so they just ignored it. I'm not really very happy with that Aristotle dude. We decided to replicate Galileo's inclined plane experiment because it was so fundamental to new concepts of motion in Galileo's time. We based our experiment on Galileo's own description of the inclined plane in his book, Discourses on True New Sciences, published in 1638. So this is Galileo's words translated to English. A piece of wooden molding or scantling about 12 cubits or 7 meters long, half a cubit or 30 centimeters wide, and 3 finger breadths, so like that wide, 5 centimeters thick, was taken. And on its edge was cut a channel, a little more than 1 finger in breadth, and having made this groove very straight, smooth, and polished, and having lined it with parchment, also as smooth and polished as possible, we rolled it along it a hard, smooth, and very round bronze ball. So in other words, that ramp that we saw, that sort of board that was up on its side. Our own construction entailed planing at a 45-degree angle, one edge each on two 16-foot 2x4s, each when nailed together to form a groove. We sanded and oiled the groove to create a low-friction effect like Galileo's parchment. Instead of a small bronze ball, we used a 3/4-inch steel ball bearing, and we added a metal piece to the end of the inclined plane against which the ball struck at the end of each run to make our timing precise. Click here for a more detailed description of our inclined plane. We also replicated Galileo's apparatus for timing the inclined plane experiment. Galileo describes his water clock in Discourses on True New Sciences. So Galileo says, for the measurement of time, we employed a large vessel of water placed in an elevated position. To the bottom of this vessel was soldered a piece of small diameter giving a thin jet of water, which we collected in a small glass during the time of each descent. The water thus collected was weighed, and after each descent on a very accurate balance. The difference in ratios of these weights gave us the difference in ratios of the time. So, Connor, try and focus on this. I know there's other girls in the room. Okay, try and focus on this. So what Galileo did was he had like a big jug of water, right? And put a pipe at the bottom, right? And then when he let the ball roll down, he rolled it down a certain length, and he timed it. He had his thumb on here, and what would happen to the water? It would come out, right? And he would collect a little bit of water, and that was his way of measuring the time. How much water was released during that time. And if there was twice as much water, well, then that was clearly twice as much time. Okay? There isn't really good records onto which timing method he used. Most people believe that he probably did it 2 different ways to see if he could come up with a better way. Okay? So he probably used the water thing for measuring. He probably used the pendulum thing for measuring as well. Okay, so what these folks did, our water clock consisted of a plastic bucket with a small hole drilled in the bottom into which we placed a length of plastic tubing. When filled with water, the bucket emitted a thin stream of water through the plastic tubing. We controlled the flow of water by clamping the tubing with a small metal clamp. We marked our inclined plane at 1/4, 1/2, and 3/4 its length. Starting with the full length of the plane, we rolled the ball 20 times down each length, timing each trial with our water clock. Like Galileo, we weighed the water from each trial so as to determine the ratio of times for each length. Our experiment proved that Galileo could have obtained the accuracy which he claimed for this experiment. Our findings also point clearly to the concept of acceleration. The ball travels down 1/4 of the plane in half the time it takes to traverse the entire plane. Aristotle would have posited, of course, that the ball's time would have been directly proportional to the distance traveled. In other words, it would have been a direct proportion. Right? It would have been half the time, it would have been exactly the same amount of time. Andrew Irving has created graphs which clarify Galileo's discovery that the ratio of the distance traversed by the ball is proportional to the ratio of the squares of the time. So in fact, when Galileo did his graph, which you're going to do tomorrow, is he would get a curved graph. Aristotle would have said it's a straight line. The only difference being Galileo actually did an experiment to do it. Aristotle just said, no, it's a straight line because I'm Aristotle. And that's that. Okay, so hopefully you're going to get a chance to do that tomorrow. Okay, and get a little better appreciation for our friend Galileo.